All right. Thank you, everyone, for being here today. Before we get started and I introduce the speaker, I just want to remind everyone to please hold your questions till the end, unless you have a burning clarification question that just cannot wait, in which case put it in the chat and then I will read it to our speaker. So today's speaker is Dr. Yifan Zhou. He got his PhD here at the University of Arizona in 2019, working with Daniela Pai. He is currently a McDonald Observatory postdoctoral fellow at UT Austin. And broadly speaking, he works on observational characterization of exoplanets. And today he's going to tell us about, all right, Yifan, the floor is yours.
Okay, all right. Is the internet connection okay from my side? Hopefully it's okay. Anyway, all right, I'm very excited today to be back, as always, sort of like virtually back to the Stewart Observatory after 1.5 years living there. So the project that I'm going to talk about today is actually started when I was a graduate student, when I was finishing up my PhD degree at Stewart. So with the help of a lot of my collaborators, including many of you at Stewart, we had this very exciting result of observing the PDS 70 system with Hubble Space Telescope. So by observing using high contrast imaging with HST to observe this system in UV and H-alpha, so we made the first ever discovery of first ever detection of a planet in direct imaging mode in the UV bandpass. So today I'm going to talk about the motivation for this observation and the technique that enabled this detection, and also discuss what we learned from this observation about the formation of PDS 70 planets as well as like giant planets in general. So to how exciting we are in this signal for planet formation from the very beginning of protoplanetary disk to the growth and to the forming and the growth of young planet, all the way to the matured planetary systems. So at the very beginning, thanks to ALMA and a lot of AO images, we have observed a lot of beautiful disks, circumstellar disks, and we found that in those disks they have very rich features, including rings, gaps, arcs, and spirals. Many believe that those structures are related to planet. It's the planet perturbing the disk create those features. So by follow those features, we can trace all the way back to the very beginning of a planet formation to study planet formation there. And at the end phase of a planet formation, the evolution, we have discovered a lot of matured exoplanetary system thanks to multiple methods, mostly radial velocity and the transit. So this large number of exoplanets, so to today more than 4,000 of them, give us opportunity to characterize their atmosphere, their orbital configurations, and which those like properties of this mature system, which are also like a consequence of the formation, the evolution of the planetary system, and we can use them to trace all the way back to their formation phase. So only until very recently, we have captured the planets that are still have their ongoing mass accreting activity. So these are very exciting discovery because they give us the opportunity to watch the planet formation in action. So we can, by observing this system, we can gain the ground truth of how do planet gain mass from its surrounding environment. So in today's talk, specifically by so the PDS-70 system has been a favorite for studying planet formation in the past decade. So the beginning of this probably is because of the rich structures that has been discovered in the circumstellar disk around the star PDS-70, which is a 5 million year old weak-line Titori star. So back in 2012, Hashimoto et al. Used high contrast imaging to observe this star and found that the stellar disk has a giant inner cavity. So the inner cavity has a diameter of about 100 AU. So in the original discovery, those authors discussed the multiple possibility for the formation of this cavity. And the most likely solution to create this cavity is to have one or multiple companions to the star to carve out materials in the disk to create this inner hull of the disk. So this encourages follow-up high contrast imaging operations to look for those possible companions. And finally, in 2018, using VLT sphere observation, Kepler et al. Found a point source that is less than 200 milliarc second away from the star. If you convert it to the absolute distance, is about 20 AU. So the point source has the color and the brightness that is the appearance of a planet. And they also found very clear evidence that this point source is co-moving with the star. So because of this very concrete evidence, so they announced that this is a planet to the PDS-70 star, and the planet PDS-70b is likely to be the reason we see this inner cavity of the disk. What's more exciting is coming from two observations. I think they both led by people here at Stewart, although I think Sebastian back then was not here. So unfortunately, I didn't meet you when you made this exciting discovery. So the first detection is made by my former office mate, Kevin Wagner. So he points the Magellan telescope using the Magellan AO system to point it at the PDS-70 using the narrowband H-alpha filter, and found that the planet PDS-70b is emitting H-alpha at a very high strength. And Sebastian Hefford, not too long after that, gained even deeper H-alpha image and found this system has not only one, but two H-alpha emitter. So this image gave us another planet around the star PDS-70 and made the PDS-70 system the only planetary system that has two H-alpha emitting planets. So the H-alpha emission from these two planets are very strong. To illustrate how strong the H-alpha emission is, we can compare to the observed flux in the H-alpha band compared to what we expect from the photospheric emission from the planet. So the photospheric emission can be constrained by the near-infrared observation of the planet. The H-alpha in the optical band is more than 3 orders of magnitude higher than the photospheric emission. So the reason that we think the planet is emitting such a strong H-alpha emission is because of the planet is accreting. So this give us so this detection in H-alpha give us opportunity to measure how fast the planet is accreting. So how fast the planet is gaining mass by come up with a way to connecting the brightness of planet in H-alpha into a mass accretion rate. So because we are trying to connect the H-alpha emission into a mass accretion rate, I think I want to take a step back to look at the idea of why do we think H-alpha traces the accretion activity onto the planet. So the idea of that we can use H-alpha to trace the accretion activity is initially inherited from the observation of Titori stars. So in Titori star, the most, so here I present like the most well-received.
Yifan, before you go on, we have a question in the chat from Josh Eisner, who asks, if there is accretion, why would we think the IR emission would trace the photosphere?
So I think if you compare to like the so the accretion-induced excess emission compared to the accretion-induced excess emission would contribute a bit to the infrared, but like compared to optical band and IR, so in the optical band, it's mostly come from the accretion-induced flux, but the IR, most of the flux are still from are coming from the photosphere. But in order to get an exact measurement of how much photosphere emission from that are emitted from IR, I think you need to introduce, count both the accretion-induced flux and the photospheric emission.
All right, thanks.
Okay, so I'll continue. So basically, in this magnetospheric emission model, we can dissect where are the flux are coming from in this model. So this model is built for like star formation. In this model, the materials are launched at this truncated circumstellar disk. So they follows the magnetic field of the star and falls all the way onto the stellar surface. So this accretion flow has a nearly free fall velocity falls onto the stellar surface. So on the stellar surface, the velocity of the accretion flow is so high, it's above the local. So it's a supersonic accretion flow onto the stellar surface. So at the stellar surface, enormous amount of kinematic energy is converted into thermal energy as the accretion front. And that heat is so high that it can ionize the hydrogen atoms as the accretion front. And the flux at the accretion front can heat both the pre-shock and the post-shock region here. That creates the most noticeable feature that we see from accreting star, which is the elevated continuum emission. So this continuum emission is coming from the this heated photosphere and the pre-shock region. If you compare the spectrum of accreting star and a non-accreting star, you basically notice that at the UV and optical region, the accreting star has large amount of excess emission. So by measuring this excess emission, we can get most of the accretion-induced luminosity from star. But on the other region is this incoming accretion flow. These accretion flow are actually where most of the emission lines are coming from, because at this either the pre-shock region or the post-shock region for the stellar accretion, they are too hot and too dense to produce significant amount of line emission. But this incoming accretion flow, on the other hand, are not dense; they are optically thin with respect to the line emission. So they are mostly responsible for the line emissions that we observed. So the observation of Titori star showed that this line emission and the total accretion luminosity, although they come from a different area of the different region of the accretion activity, they are correlated. Both the luminosity of the line emission, here I show the example of H-alpha line emission, and the line width, they are empirically, they are correlated with the total accretion luminosity. So this provides us to measure the accretion rate without observing the entire spectrum to determine the total accretion luminosity. However, we can see the most of the accretion luminosity, they're not coming from the same region. So to have like a complete theoretical explanation and to reproduce this correlation theoretically is actually not straightforward. And I don't think we have a very satisfied solution yet. So because of that, it's not clear to us like how far we can extend this relation outside of this T-Tauri star accretion regime. But for PDS 70 per se, because we only have the measurement in H-alpha, perhaps the best way we can constrain is its accretion rate without any other observation is by extending this relation. But I want to now give a very naive picture of how I think planet formation, how this giant planet accretion happens, and try to motivate you that to only observe H-alpha may not give us a complete picture of in order to measure the accretion rate. So to compare this giant planet accretion regime and the stellar accretion regime, we can think of like the planet accretion is like a scaled down version of the stellar accretion. So the planet may have enough magnetic field to support magnetospheric accretion. These are supported by like theoretical calculations and by like rotation constraints suggest that the planet should have enough magnetic field to support such kind of accretion. So we can think of it like embedded. It's like a scaled down version of the stellar accretion embedded in the circumstellar environment. So because of the planet is embedded in like a circumstellar disk, so the accretion fronts can occur on both the surface of the circumplanetary disk and the planet. These are not likely to be like very important in the case of PDS 70 because from our observation of this system, we learned that the circumstellar environment at the location of the PDS 70 planets, they're mostly empty and do not have a lot of mass for the circumplanetary disk to gain mass from. However, the other part of the difference are more important. So because of the lower mass of the planet and the lower gravity from the planet, the accretion flow are weaker compared to the stellar regime. So the velocity of the accretion flow are lower. So the kinematic energy of the accretion flow are lower as well. So because of the weaker accretion flow, they may not have enough energy to completely ionize the hydrogen atoms as accretion front. So at the post-shock region on the planetary surface, the hydrogen atoms may not be completely ionized and they are not as dense as those in the stellar regime. So they may be able to also produce line emission for us to trace its accretion activity. So because of this kind of like a difference, we may question whether those correlations gained from star formation studies can be extended into the planetary regime to get like accurate measurement for the planet. So in order to have like a more direct measurement of the planetary mass accretion rate, we may want to try to think of a way to skip this correlation and measure the accretion luminosity more directly. So if we look at the difference between a accreting star and a non-accreting star, we think that if the planet's spectrum follows in the same manner, the best way in order to constrain like the excess emission that are induced by the accretion activity. It's perhaps to trace it into the optical and even best in the UV band. So the advantage of UV image is that most of the accretion-induced flux, their contribution increase if we go to lower wavelength region. And if we can target the object at the wavelength that is lower than this Balmer jump, we'll have some constraint of the Balmer jump coming from the hydrogen continuum emission from the planet. And so this kind of observation to take a photometry at the UV band to measure the accretion-induced luminosity has been applied to measure the tiny accretion rate onto brown dwarfs and the substellar companions previously. So this method should also work for PDS 70. So to summarize the first part so far, basically the motivation to carry out the observation is that we are not sure whether the correlation between the H-alpha line and the total accretion luminosity gained from the star formation studies can be applied to planet formation. So we want to get a more direct measurement for the total accretion luminosity. So that requires us to target the planet to get the photometry of the planet at the UV band. However, it's a very challenging task because we need to take a diffraction limited image in the U band with the telescopes because the AO correction are not as effective at lower wavelengths as they are in the near infrared. So we need to use a space telescope here. Basically, the only available instrument we can use is Hubble Space Telescope. But we also noticed the challenges coming from the high contrast. So I'll explain this with the image of PDS 70 taken with Hubble. So if we convert the separation between the planet and the star, so the separation is less than 200 milliarcsecond. If we convert it, the separation is less than 5 pixels. And notice that also the brightness contrast between the star and the planet is huge. It's more than 1,000 times. So in this image of a PDS 70 without any post-processing, you can see this expected position of the planet is pointed out by this small arrow. You cannot see the planetary signal at all because the planet is so close to the star and is so much fainter than the star. So there is to get a very precise constraint of the shape of the point spread function of the star so that we can remove it very clearly from the image so that we can review the image of the planet. Luckily, I think I learned quite a lot of tricks as a graduate student at Stewart. So the way we can turn HST into a high contrast imaging machine is by applying the techniques that we used in ground-based observation into space-based observation. So the key here is to conduct this angular differential imaging observation. Here I showed a simple example of how to conduct angular differential imaging with Hubble. So you observe the same field with 2 different telescope roll angles. So the actual astrophysical scene, because you are rotating the telescope, appears to be rotating relative to the structures that is fixed onto the telescope. So by subtracting the 2 images taken with different telescope rolls, you can differentiate the astrophysical scenes that are rotating between these 2 images from the PSF structures. So if you subtract these 2 images from each other, astrophysical signal here is this point source from a close companion preserved, while the image of the star is pretty much subtracted So in this case, there is still quite a bit of residuals because we only use two angles for this simple example. So for the observational PDS-70, we conduct 18 orbits of angular differential imaging observation. So in each orbit, we have the telescope rolled at different angle. So our observation have 18 different roll angles to map out the shape of the PSF. So we conduct the observations in two bands in the UV and H-alpha. So they are almost observed simultaneously, two bands. So the total integration time is much greater in the UV band because we expect the signal in the UV is lower. The H-alpha emission from the planet helps to increase its signal quite a bit. So we only apply the less than 1 hour of integration time in H-alpha. So in order to to map out the PSF of the star very precisely, we also adopt a suite of image processing techniques that are developed in ground-based observation and also for HST as well. So the first important algorithm that we included in our observation is the analytical PSF reconstruction algorithm. So the wide field camera 3 detector for Hubble is not initially designed for this kind of tiny field of a point source. So the PSF, so the original PSF is not Nyquistly sampled, but luckily there is like this analytical algorithm available that are developed 20 years ago that can give us a guaranteed Nyquist sampled PSF so that we can apply the subsequent PSF modeling algorithm into it. So we use this method to combine a set of 4 images to double the spatial sample rate of the image to get a analytically approved Nyquist sampled series of Nyquist sampled images. And we applied this angular differential imaging technique. So we have a suite of 18 images. They are self-contained PSF libraries. For each one of the image, the other 17 images can serve as PSF images for the primary subtraction. So we also adopt a suite of a very well-developed and well-tested method that are used in ground-based AO observation into our space-based observation that includes CLIP algorithm, which give us the most optimized linear combination of the PSF image for the primary PSF subtraction. And we also use additional method to calibrate the photometry so that the photometry is not affected by the PSF subtraction processes. And we use other additional methods that help us to estimate how significant and how robust our detections are. So all those methods, they are very well tested in ground-based observation. We just need to borrow them for our space-based observation studies. So here are the images before conducting the PSF subtraction. You basically will see 2 very boring point source image, one in UV, one in H-alpha. Without any post-processing, you only see the signal from the star. But after applied the method I mentioned before, you see now at the bottom left corner of the star, there is a point source popped out. They appeared at the same position in the 2 images, in the UV image and in the H-alpha image. So the position of this point source matches exactly of the position we expect from PDS-70b, the planets. And both of the point source, they are more than 5 sigma above the background. So because of this line of evidence, we are very confident that this source is corresponding to the emission from the planet. So this marked the first direct detection of an exoplanet in UV. So in the UV band image, you also notice at very close to our inner working angle, there looks like a close companion, which actually has been identified previously in near-infrared observation of this of PDS 70. So based on the spectral energy distribution of this close companion, it looks like a scattering source from circumstellar material. So we will not discuss about this source too much in this talk, but focus on the signal from the PDS 70, the planet. You also notice that we didn't detect the PDS 70C. So the PDS 70C was initially discovered by Sebastian Heffert et al. In 2019 using BLT and subsequently confirmed by various studies. However, the discovery of the planet PDS 70C was announced after we proposed for this observation. The planet C is only 30% as bright as B. So our integration time was not designed to observe it. So if you compare the expected brightness of a PDS 70C to our detection limit, the solid line here is representing the 5 sigma detection limit, and the dashed line representing the 3 sigma detection limit. You see the expected signal is below our detection limit. So the non-detection is expected, does not contradict with the previous observations. So just unfortunate that we didn't propose long enough observing time to get the detection of PDS 70C. So let's focus on B. So what we can learn from our observation. So what our observation provides us is 2 photometry for PDS 70B, 1 in H-alpha, 1 in the UV. So if you compare to the near infrared emission, which determines its photospheric emission, these 2 photometry points, they are significantly higher than the expected photospheric emission. So that says that in the UV and in the optical band, the observed flux are dominated by the accretion-induced excess emission. So the UV band help us to constrain the amount of a continuum emission that are coming from the accretion shock. So here to model the emission from the accretion shock, we use a very simple plane parallel pure hydrogen LTE model to give us the shape of the continuum emission. So we can use our newly measured U-band photometry in this green point to constrain the strength of this continuum emission. So these 2 photometry points can help us to measure to derive its accretion luminosity from the planet. So in order to derive the accretion luminosity, we split it into 2 parts. So the first part, we assume it has this line emission, and here for the H-alpha line is quite straightforward. We just need to integrate the total flux within the H-alpha band and calculate the H-alpha luminosity. Here we neglected other lines, which can introduce not a negligible amount of uncertainty, which I will discuss later. But for now, I will just assume the line luminosity is the same as the H-alpha luminosity. For the continuum part, we use this plane parallel hydrogen model as a bolometric correction for the U-band photometry, so that we integrates the total amount of flux within that model and calculates the amount of luminosity that is corresponding to this continuum model to get the continuum luminosity. Another important assumption I assumed here is there's no line of sight extinction, which can also introduce quite a bit of uncertainty, which I will discuss later. So this gives us a nominal accretion luminosity that we can measure from our observation, which is about 1.8 times 10 to the minus 6. So let's take a look at the possible systematics in this measurement. So the first thing you notice here is if you take the ratio between the H-alpha and the continuum luminosity, the H-alpha contribution is very significant. So the H-alpha is about 60% of the continuum emission. So in the previous study, we found observations of a brown dwarf, of a accreting brown dwarf and a planetary mass companion. We found this, there is this like loosely anti-correlation between the accretion rate and the H-alpha contribution. So the lower the accretion rate is, the higher the H-alpha contribution there is. So the measurement for PDS 70 B from our nominal measurement falls onto this correlation exactly. But for most of the stars, the line contribution can be pretty much ignored because the line contribution is below 1%. It's like at this region outside of the outside what we plot the y-axis range in this plot. So this can suggest a possible different radiative transfer mechanism between the accretion onto PDS 70 and the stellar accretion. So for PDS 70, it's possible that because of the H-alpha line can come from both the pre-shock and the post-shock region. So the line emission are much more important than what we observed in stellar accretion. So the implication for measuring the accretion rate is that because of the line emission are much more important in the case for PDS 70, we can probably ignore it, the line emission in stellar observations, but not for the observation of PDS 70b. So if we neglected those lines, that may lead to an underestimated result for the accretion rate measurement. So the way out probably is to have a model that can give us if we can measure H-alpha, that can give us an answer of what other emission lines are, so that we can include all the lines to get a more accurate result for the accretion luminosity measurement. Another source of uncertainty is the assumption of zero extinction. So if we assume a non-zero extinction at such a short wavelength in the U bands, the non-zero extinction can introduce a large amount of derating factors. So the A sub V of 3.3 would corresponding to a greater than 100 derating factor that would increase our accretion luminosity and accretion rate measurement by more than 2 orders of magnitude. So there has been arguments for high extinction for the planet. It's mostly coming from the non-detection of H-beta lines from the planet that relies on a theoretical line ratio between the H-beta and the H-alpha. So if we use this high extinction rate estimate for our accretion luminosity and accretion rate measurement, because of the extinction affects the U-band photometry much greater than H-alpha. So the accretion luminosity measurement increase much steeper than only accounts for extinction for H-alpha. So the A sub V of magnitude of 3 would increase the accretion rate estimated for the planet to more than 10 to the minus 7 Jupiter mass per year. That is on the same order or even higher than the average the mass growth for the planet derived by the mass divided by the age of the system. So this is a quite a significant source of uncertainty. I think we need a theoretical measurement for how bright the planet's supposed to be in the U band, so that we can use our U band detection to have a tight constraint on the amount of extinction for the planet. So just to now we get the accretion luminosity. To convert the accretion luminosity into the accretion rate, we can equate the kinematic energy of the accretion flow, which is related to the free fall velocity of the accretion flow and the measured accretion luminosity. We equate the two part, we can get the mass accretion rate, which is related to the radius and mass of the planet and our measured accretion luminosity. So we insert the mass and radius constraint from near-IR observation and evolutionary models and our observed accretion luminosity. We can get a accretion rate measurement, which is about 1.4 times 10 to the minus 8. So just to put this measurement into context, for star formation studies for like a star, we have this correlation between mass accretion rate and the mass. So how do the measurement for PDS 70b falls onto this relation? It's here. And as I mentioned, our like a caveat in this measurement would all probably make this result underestimate. So the accretion rate may be even higher. It shows that the measurement for PDS 70b is significantly higher than the correlation we get from star formation. So that may suggest that in the formation of PDS 70b, because it has a large mass reservoir from the circumstellar material, it gives the planet relative to its mass the higher mass accretion rate. So perhaps this premium sequence star is not a very good analog for PDS 70b. Perhaps those like class 1 like objects that are still embedded are much better analogs to understand the formation mechanism for the planet. So the last point I want to mention is about the variability of PDS 70b. So in the previous two ground-based observations, the H-alpha H-alpha flux from the planet is different by a factor of 4, although it's less than 2 sigma, but this difference is quite significant. So it's possible evidence for H-alpha variability. So in our observation, our entire observation time baseline is nearly 5 months. So we can have like a time resolved photometry light curve for PDS 70b from our observation. So what does it look like? It looks like this. So we don't have good evidence for variability in H-alpha for PDS 70b. Our measured flux is in between of the two previous H-alpha measurement, but within our HST observation, there is no clear sign of large amplitude variability. We need to notice that the primary star is variable. In ground-based observation, correct me if I'm wrong, I think the brightness of the planet is calibrated by the brightness of the star. So if the star is variable, the photometric calibration of the planet not be as accurate. So I would argue that because we can gain absolute photometry from HST, and HST are a very reliable, have very reliable this time resolved photometry observation. So I think the best way to categorize whether the planet is variable in its accretion related features is to have a dedicated observation to monitor whether the planet is variable or not. So I will skip this slide since the time is up and come to my summary slides. So to sum up, so for the first time, we directly detect a planet in UV. Our UV measurement constrains the hydrogen continuum emission for PDS 70b, and use H-alpha and the U-band observation, we get a new mass accretion rate measurement. Although our, as I mentioned before, this mass accretion measurement have its own caveat, because we don't have a very good extinction constraint, and we neglected other line emissions. So this two caveat may like increase the actual estimate for the mass accretion rate. So we get a very high ratio between the luminosity of H-alpha and the continuum emission, suggests that there may be radiative transfer mechanism difference between the accretion onto PDS 70b and in general giant planets versus the accretion onto a star. Our time resolved observation didn't see evidence for H-alpha variability, although our the precision of our light curve is still quite low. So I think it's encouraging to have a dedicated monitoring program to monitor whether the planet is variable or not. So that's all for my talk. Thank you very much for your attention. I would like to take any questions.
All right, thank you so much, Yifan. If you have a question for the speaker, then I ask that you please either use the raise hand feature under reactions, or you can type your question into the chat. Ben.
Hi, Yifan. Nice talk. I wonder if you have any plan to do you think that it's possible to pin down the extinction using different photometric bands on HST, or even to have a longer exposure to going deeper in the sensitivity and to try if you can detect the PDS 70C or not?
I think the other band would be very challenging. So if the SED of the planet, it's behaved exactly the same as what I plotted here. The other optical band would have a very high contrast between the planet and the star. So to get a 5 sigma detection in the U band, which is helped by this Balmer jump, we already need like 18 orbits of HST time. So to observe it in other optical band, that would ask for probably double or even triple the telescope time to get a detection. So I would say that is very challenging. Maybe the ground-based like VLT Muse observation, if they can like probe even deeper. I don't know if Sebastian has a plan for that. That may give us a good constraint on the extinction for the planet.
All right, Sebastian.
Oh, yeah, it was a very nice talk and great result. Yeah, do you think it's possible to do the H-beta line with HST? Because I mean, as you said, I've done a very long deep integration with Muse. So I've increased exposure time by a factor 20. But the constraint that I currently have is that I have a 3 sigma upper limit of a 1:10 line ratio of H-alpha to H-beta. So, and to get anything deeper, it's very difficult with VLT Muse, because then I would need to integrate for multiple nights. So
yeah,
wondering
so
if
it's possible to. So on HST, it has this narrowband H beta filter, which should be very helpful to conduct such observation. I think in order to have like a competitive proposal to have H beta observation for PDS 70, I think we need to we should like discuss like why HST, like the HST can give us a stronger constraint than like this very long like a ground-based exposure. I wonder if, for example, if the fact that HST gave us this like a diffraction limited image by for free compared to like ground-based AO observation, it has its own advantage in doing like H beta observation for PDS 70. If that's the case, I think we should make a very promising proposal for like next cycle to go after this with H beta lines.
Yeah, because I think the detection of an H beta line would really help to pinpoint the extinction. Because if you have the UV measurement in H beta and H alpha, then
yeah. So I think that sounds like very exciting to me. We should discuss offline if we should like write a proposal together to follow it up with H beta or with HST.
Sure. Okay. Thank you.
All right. And we have a slew of questions in the chat. So the first one is from Zhaoan, who says, great talk. Planet potential is shallower than the star, so the accretion shock temperature will be lower than that of the protostar. What is the accretion shock temperature you derive from your slab model? With this temperature, what is the filling factor of the accretion shock?
So here, I think the slab model I applied here is like a very simple model, and we didn't, because we only have this like one photometric point. We cannot even constrain like the size of the Balmer jump. So it's very difficult to constrain like the temperature of the accretion shock and the filling factor here. So pretty much the slab model applied here is used only for like volumetric correction for this U-band photometry. So we don't have a very good constraint on the temperature and the filling factor. I think the way forward here is to have like a multiple like accretion related features, like for example H beta, so that we can H beta and perhaps other hydrogen like emission lines. After we get that can give us a better constraint from observation to get the temperature and the filling factor for the accretion shock.
All right. Next question is from Jayhan Bay, who says, thank you for the nice talk. I wonder if we can completely rule out the contribution from accretion shocks onto the circumplanetary disk. Is there a way to observationally distinguish shocks on the planet versus the disk?
So in this case, I think there's like a recent paper from Aoyama et al. Discussed if both shock occurred, both a shock on the CPD and the shock on the planet, both shock occurred. It should be the case that the shock on the planet would dominate the observed flux. And it looks like from that model, the most difference between the shock on the CPD and the shock on the planet, they differ the most on this Balmer jump. So the higher, so the shock onto the planet would give us a higher Balmer jump. So if we could have like a very like quantitative prediction of the Balmer jump from these two shocks, I think we can use this U-band detection to help us to rule out if there is any, if we observe any flux from the shock onto the circumplanetary disk.
All right. Next question is from Joe Negeta, who says, lovely results. Is the accretion rate onto the planet expected theoretically, the high accretion rate? And what does it tell us about the system?
It depends on like the accretion rate. I think like which accretion rate that we are discussing here. So if this nominal measurement, this accretion rate is much lower than like the average mass growth is derived by the mass divided by its age. So this accretion rate probably shows that the planet is relatively at its like a tail end of its formation phase. So if we use this like a high extinction assumption to get the accretion rate for the planet, it gave us a accretion rate measurement that matches the average like the mass growth for the planet. That would suggest that the planet is still actively accreting. So in terms of like whether theoretically like the magnetospherical accretion onto the planet can create such a high accretion rate, I'm not clear. I'm not sure about whether we have a good prediction here. So if anyone from the audience that can help me answer that, that would be great.
All right. And then we have a question from Neil Turner, who asks, what does the UV detection tell us about the circumplanetary disk geometry? Hydrodynamical circumplanetary disk models are quite geometrically thick.
So yeah, I need to think about this, because I think so far the prediction for like accretion for like a planetary accretion to produce this like this hydrogen continuum emission, the theoretical study, as far as I know, are quite limited. So I need to like perhaps to think more carefully to or like read more to see like what would be the theoretical case for like a circumplanetary disk in order to produce such an emission. Yeah, I'm not sure about the answer to this question.
All right, and that makes us end perfectly on time. Excellent job. So thank you all so much for coming today. We will see you at the next talk. Bye.